Hello everyone. So today we're going to go over section 3.3, reciprocal of a function. So the function we'll be looking at are linear function and quadratic functions, and then their reciprocals. So let's look at example 1. Sketch y equals x and then y equals 1 over x. As you can see here, we already have the graphs. In purple we have y equals x, and then in orange we have y equals 1 over x. So just be sure to label that. So let's talk about how these graphs came to be. Um, y equals x should be fairly clear at this point. So let's dive directly to y equals 1 over x. Again, we just simply take the x values and find their reciprocals. So for example, when x is equal to -2, then y is equal to -1/2. The reciprocal of -1 is -1. The reciprocal of -1/2 is -2. The reciprocal of 0 is undefined. And then we have 2, 1, and 1/2. Now when those points are plotted, the orange graph is what results from that. A couple of important things to note here. Number one is the non-permissible values, and this refers to the non-permissible x values. So basically, this happens when the denominator is 0. So in this case, the non-permissible value would be that x cannot be equal to 0 in this graph, and that results in an asymptote x equals 0. Okay. Next up, we have the invariant points. So that's when the points are the same from y equals x to y equals 1 over x, and there are two invariant points, 1, 1, and also -1, -1. Okay. Another asymptote that we have that's already drawn on here is y equals 0. And to understand why y equals 0 is an asymptote, you have to consider that if y was equal to 0, then y equals 1 over x would become 0 is equal to 1 over x, and there is no x value for which this equation works. So there's no solutions here. As a result, the two asymptotes that we have are x equals 0, which is a vertical asymptote, and y equals 0, which is a horizontal asymptote. And the domain and range, in this case, corresponds to those asymptotes, so x cannot be equal to 0 is our domain, and y cannot be equal to 0 is the range. Okay. So here is the same graph drawn on Desmos. Again, we began with y equals x, the original function, and then we take its reciprocal, and this is the resulting graph, as we saw in the notes as well. And the two asymptotes at y equals 0, the horizontal asymptote in green here. It's a little bit hard to see. Here we go. And then the vertical asymptote at x equals 0 as well. All right, so the important thing to note here is that the invariant points 1, 1, and also -1, -1. Okay, so next we have example number 2. Sketch y equals to 1 over 3x minus 2. So once again, in purple, we have the graph y equals 3x minus 2. And in orange, we have the reciprocal function, so that will be y equals to 1 over 3x minus 2. Okay, so important things to note here. Let's go back to Desmos and look at the graph. Here we go. So here is the original 3x minus 2 with the y-intercept of -2 and the x-intercept of 2/3. And then we have the reciprocal function. Notice that instead of the vertical asymptote being at x equals 0, it's going to be at x equals 2/3 this time. And we'll talk more about how that works algebraically in just a bit. And then y equals 0 is the horizontal asymptote. Okay, and we can also look at the invariant points here as well. And they will be 1, 1, and then 1/3, -1. So, again, to obtain this graph, probably easy to just use a table of values or to draw the original function, the 3x minus 2, and then take the reciprocal, make a table of values, and plot that graph. And then find the non-permissible values and invariant points, and therefore the asymptotes and all of that using algebra. So let's go back to the notes section to have a look at that. So the non-permissible value, once again, happens when when the denominator is equal to 0. So in this case, we have 3x minus 2 is equal to 0. So that would be 3x equals 2. So x cannot be equal to, actually this should just be cannot be equal to 2/3, which is what we have here for the asymptote. And here, y equals 0 is the horizontal asymptote, which makes sense because, again, similar to the previous example, if we have 0 is equal to 1 over 3x minus 2, this has no solution. Okay. So going back to the invariant points part, the invariant points happens when the original function 3x minus 2 and its reciprocal are equal to each other. So algebraically, it would look something like this. So if we were to solve for x, we multiply both sides by 3x minus 2. So 3x minus 2 squared is equal to 1. We then simply take the square root of both sides. So 3x minus 2 is equal to plus or minus 1. Then we add 2 to both sides. So 3x is equal to 2 plus or minus 1. So that means x is equal to 2 plus or minus 1 all over 3. Alright, so if it is 2 plus 1, then 3 divided by 3 will give us 1. And if it's 2 minus 1 in the numerator, then we'll get 1/3. Okay. And then, of course, we substitute this into either the original y equals 3x minus 2 or the reciprocal. Either way, that will produce the invariant points. And so, if we substitute in 1, 3 times 1 is 3, minus 2 is 1, so that will give us the point 1, 1, as we saw on Desmos. And then 1/3, well, 1/3 times 3 is 1, 1 minus 2 is -1, and that will give us the point 1/3, -1. Alright, and the domain and range, of course, corresponds to the asymptote that we saw earlier, so x cannot be equal to 2/3, and y cannot be equal to 0. Alright, so that's example number 2. Let's move on to example number 3, which is a little bit more complex because we are dealing with the reciprocals of quadratic functions, and the graph is a little bit messy here. There are basically 4 graphs on the same grid, but we'll examine them one at a time. So for clarity's sake, the lighter purple graph and the orange graph are a pair, and the darker purple and the red graphs, they are a pair. So we'll also look at it on Desmos, and that should clear things up a little bit. All right, also helps to maybe label everything. So um, the orange graph is y equals 1 over x squared, and the red graph, that is y equals to 1 over x squared minus 4. Righty, and the other calculator that we use is green, so there is the asymptote x equals 0, and then there's a second green that we use, the y equals plus or minus, sorry, x equals plus or minus 2 is the vertical asymptote for the second graph. Um, so a little bit more complicated, but hopefully we can clear this up with looking at it on Desmos and also using a table of values. All right, so let's focus on just y equals 1 over x squared. All right, and we'll make a table of values here. So if x equals to negative 2 squared is 4, and the reciprocal of that is 1/4. And then likewise, negative 1 squared is 1, 1 over 1 is still 1. And then the square of negative 1/2 is 1/4. The reciprocal is 4. And then, of course, this is once again undefined. So, and then 1/2, 1, and 2, the square and then reciprocal will be 4, 1, and 1/4 respectively. So notice that in this case, the square on the x value makes it so that any x value square will be positive, and then we take this reciprocal. So the orange graph is entirely above the x-axis. Okay. So the non-permissible value, well, we have x squared cannot be equal to 0. So x cannot be equal to 0. That's easy for the first graph. And then for the second graph, the graph that was in red. Oh, sorry. Before we move on, and of course, this table of values on the right here is what we use to graph the orange graph. And if we look at this on Desmos, let's go on to the next one. Yeah, so this is the original y equals x squared, the parabola, of course. And then we take the reciprocal of that, and looks very much like the orange graph that we have. We have the invariant points, 1, 1, and negative 1, 1. We'll examine how that works in just a bit. And of course, the asymptote y equals 0 and x equals 0. Yeah, so let's go back to the notes. Right, so the non-permissible value x cannot be equal to 0, so that will give us the asymptote. Also, notice that, well, if 0 is equal to 1 over x squared, again, that gives no solution. So that's why y equals 0 is once again asymptote as well. So make a note of that here. So that would be x equals 0 is an asymptote, y equals 0 is an asymptote for the orange graph. And the domain and range. So the domain of the y equals 1 over x squared graph is that x cannot be equal to 0. And its range, notice that all the y values are positive. So simply the range is y is greater than 0. It cannot equal to 0 either, right? And it cannot be negative. So that's a little bit different. And now we are looking at y equals 1 over x squared minus 4. Again, let's first look at the non-permissible values. Oh, we should also look at the invariant points on, do we need to do that? I mean, to find the invariant points on the orange graph, we have x squared is equal to 1 over x squared. And if this were solved, we get x is equal to plus or minus 1, which means the invariant points would be then 1, 1, of course, and also negative 1, 1, and as we saw in Desmos as well. Okay, so non-permissible values for the red graph now. Of course, that means x squared minus 4 cannot be equal to 0 because that's the denominator of y equals 1 over x squared minus 4, which is the red graph. That means x squared cannot be equal to 4. And if we take the square root of both sides, that means x cannot be equal to positive or negative 2. And that, of course, produces the asymptotes that we see in dark green there. Let's make sure to write that down. Oh, this is the darker green. X equals plus or minus 2. Okay, and then the second piece, 0 is equal to 1 over x squared minus 4. Again, this produces no solution. So y equals 0 is also an asymptote for the second graph as well. About the domain of the second graph, of course, x cannot be equal to plus or minus 2. And the range is a bit trickier. Okay. So notice that y is greater than 0 on one side, and that is the side that's above the x-axis. And then on the other side, we have, excuse me, this shape here. And that actually has a maximum value. So y is going to be less than or equal to that value. And that will be negative a quarter. And that's what happens when we let x equal 0. That will give us the maximum value on that side. So let's say we're equal to negative 1 quarter. Okay, and the other piece is the invariant points. Again, very similar to the previous example, that can be done algebraically, and I guess we can get them on Desmos here. So the next graph here is x squared minus 4. Here is the reciprocal, and then we have the asymptotes x equals 2, x equals negative 2, and y equals 0. And of course here the maximum value, as we can see, is it was negative 1 quarter. And in this case there are actually 4 invariant points, 1, 2, 3, and 4. And it's best to find those algebraically, but we don't need to do that in this case. Usually, unless the question specifically asks for the invariant points, they are usually just used to help us draw a better graph. Alrighty, so back to the notes. We have 2 more. Y equals to 1 over x squared plus 2x plus 1, and also y equals to 1 over x squared plus 9. So the orange graph is y equals to 1 over x squared plus 2x plus 1. And the red graph is y equals to 1 over x squared plus 9. Okay, again, the best way to graph these is to make a table of values. There are some things to talk about for both of these, so let's go ahead and do that. It says here, identify any asymptotes or intercepts. So let's look at the first graph, y equals to 1 over x squared plus 2x plus 1 first. Notice that that can be rewritten as y equals 1 over 2 x squared, sorry, x plus 1 all squared. It is factorable. So if we look at the non-permissible values part, which is usually how we find um, the vertical asymptotes, then we want to look at x plus 1 all squared cannot be equal to 0. So we have square root of both sides. That means x plus 1 cannot be equal to 0. That means x cannot be equal to negative 1. And of course, that asymptote is already included on this graph. So here we are. X equals negative 1 is the asymptote that we have. And as well, this has no solution, just like before. 0 equals to 1 over x plus 1 all squared has no solution. So that means y equals 0 is a asymptote as well. So that is x equals to negative 1, y equals 0 for the asymptotes. Notice in this case there's an x-intercept that we can find for the function. Or is there? Oh, there isn't one, right? We just show that there isn't any x-intercept through looking at this part right here, right? To find x-intercept, we let y equals 0, and we already demonstrated that. If we let y equals 0, there's no x that exists that make this equation work. So there's no x-intercept for this graph. Y-intercept, so that's when we let x equals 0 to find the y-intercept. So we have y equals to 1 over 0 plus 1 all squared. So y is just going to be equal to 1. And this point right here, that is, of course, the y-intercept. All right, so let's continue talking about the graph. What else were we looking for? Oh, domain and range. So the domain and range of this graph, domain, clearly x cannot be equal to negative 1. And the range, the entirety of the orange graph, and that is y equals to 1 over x squared plus 2x plus 1, is above the x-axis, so this would be y is greater than 0. Okay. Again, if we look at it on Desmos here, here's the original function, here's the reciprocal, and we have the asymptotes. And the invariant points are 0, 1, and negative 2, 1. Again, that could be found algebraically. Right, finally, the last graph is y equals to 1 over x squared plus 9. Okay. So, notice that if we are to look at that one, let's see, does it have any non-permissible values? Okay, so if we are to look at that function that, and we're trying to find non-permissible values, we have x squared plus 9 cannot be equal to 0 to find the non-permissible values. X squared cannot be equal to negative 9. So there are no x value for it which this works. So there are no non-permissible values. So which is kind of a double negative, which means all x values are permissible. Okay. And then we are looking at the x-intercept, so let y equal 0. And so this would be, wait a second. Yeah, so next part, 0 is equal to 1 over x squared plus 9. So again, this has no solutions. So again, same thing here, none. And then the y-intercept for this graph, for the second graph, would be y equals to 1 over, uh, well, 0 squared plus 9. So the y-intercept is just 1 over 9. And then the asymptotes for this graph, it doesn't really have a horizontal asymptote. Um, it does have a, sorry, it doesn't have a vertical asymptote. It has a horizontal asymptote at y equals 0. And the domain range, well, domain is, actually, let's just double check the graph on Desmos here. Right, so here's the x squared plus 9 graph in red, the reciprocal graph. Here we have it. And then the asymptote underneath. So here's the y-intercept 0 and then 1 over 9. Okay, so going back to the notes, it says we found no non-permissible value, so the domain of that graph, and that is y equals to 1 over x squared plus 9, right here. Since it has no restrictions and its domain is x is an element of the real numbers, and then the range, um, it is going to be greater than 0 but less than 1 over 9. Well, less than or equal to 1 over 9. So if we were to write this in interval notation, then the 0 will have a round parentheses, and then the 1 over 9 would have a square bracket on that side because this is included. Or we can write it as 0 is less than y is less than or equal to 1 over 9. Alrighty, so that one is a little bit involved, unfortunately, because of kind of wanted to save some paper, so multiple examples are appearing on the same grid. Hopefully that wasn't too confusing with using colors, but that is it for today, so thank you for listening.